podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about energy, a concept that we have mysteriously been avoiding for the first couple chapters, and here it is. So, Mr. Sadler, what do you think energy is?
Energy is like solar energy, something that powers the universe, right?
So
Electricity is energy.
yeah.
Coal gives us energy. Food we eat gives us energy.
So energy is the ability to do work. And by using the words energy and work, these are both physics concepts. And you can see that the two are related, but they're not the same. You can't define a word with itself. And when we do work, we are releasing stored energy. So work is the release
Of energy.
of stored energy. And so we see our definition again in how it reciprocates. Now, when we talk about work, we're not talking about I had to go to work today for 5 hours. We're talking about doing something to release stored energy. Your muscles do physics work. Okay? So every time you're in the weight room and you move a weight, you're doing work on that weight. You are releasing the stored energy of your muscles from eating. And of course, we talk about the energy cycle, and that's done in biology and chemistry and some other places. But the whole energy cycle, the sun makes plants grow,
Right.
and then we eat the plants, and that gives us energy. And the idea here is that energy is conserved. What does that mean?
It means that the energy that the sun gave to the plant is actually being used. It's being the same energy exists.
Correct. So the same energy that's in the universe right now is the same energy that was present at the beginning of the universe. And that's a really hard idea to get our brain around because we constantly we think of that energy as lost. But Richard Feynman, who I mentioned in my class the other day, we have favorite baseball players and favorite rock stars. Well, my favorite physicist is a guy named Richard Feynman. Feynman did a lot of things. He worked on the Manhattan Project. You should look that up. I'm not going to tell you what it was. He won a Nobel Prize in physics after that. Probably should have won a second one. When I was a kid and the Challenger exploded, I actually got to see that on TV. He was the scientist that came on the TV and explained what had happened to the Challenger and why it exploded. And he passed away shortly after that, I think in the late 80s. But Feynman has this great energy explanation. He defines energy like my son's wooden blocks that he plays with and builds with. And so at the beginning of the day, my son has, let's say, 16 blocks. And he plays with those blocks. And at the end of the day, my wife and I make him pick up. And some days, we only find 15 blocks. And my son is very particular about his stuff, and he wants to make sure that he has all of it. And we look around, and sure enough, we find the 16th block. He wakes up the next morning, he plays with the blocks, he goes to school, he comes home, then sure enough, it's time to pick up, and we only can find 12 blocks. So we look around. Hey, there's number 13, 14. We found the 16th block. Number 15. There it is. And it seems like a strange analogy, but at the beginning of the day, if my son had 16 blocks, at the end of the day, he still has 16 blocks. We may have difficulty finding them, but we just have to look. The blocks are like energy.
And the conservation of energy.
And the conservation of energy. Whatever we have at the beginning is what we have to have at the end. You can't lose it. You can't gain it. You can't create it. You can't destroy it. It's one of those things that's there.
I think in chemistry you talk about the conservation of mass. Mass cannot be created or destroyed, and it sounds like energy. We have the conservation of energy. Energy is not created or destroyed. It's just changing forms.
Changing form. And actually, this is what Einstein did, on a little side note. Einstein equated energy to mass and said that they were one and the same, because he saw that, hey, look, we have these two conservation laws in science, and if you work with them enough, you get energy mass equivalence. That's another story for another day.
If we could do that, we would win the Nobel Prize.
Yeah, if we could
convert
physically do that,
mass
yeah.
into
I wouldn't
energy.
be teaching.
Yeah, exactly.
So that's Feynman's explanation. I think it's a great one. You guys, in your investigation today, did some stuff with bendy rulers, and you saw what we like to call potential energy.
So we always call that stored energy.
Right, and I think that's one way to put it. There are two kinds that we talk about in physics. One is due to gravity, so we call it gravitational.
Potential energy.
Your book will often call it GPE. And the other is elastic potential energy,
Like in a spring.
like in a spring or the bendy ruler, a rubber band, a bungee cord, etc. So this is due to a property of the material, like a pole vault. This is due to your position above the ground. Potential meaning the energy is there, it needs to be released. So in the gravitational case, you need to drop the object or release it from its height. In the elastic case, you need to release the energy from the material. So you need to snap the rubber band, you need to stretch the bungee cord and then let it go, things like that. Then there is kinetic energy, which I know is talked about in chemistry.
Yeah, well, even in PE, you talk about kinetics.
Yeah, kinetics. We talked about kinematics. Maybe that's not a term we used in Chapter 1. This is the study of motion. Well, this is motion energy.
A baseball or car moving towards you has energy
Yeah.
because of its motion.
Anything moving, big or small, has kinetic energy. And the last type of thing we're going to talk about, it's not energy, but it's related to, we talked about it in the first couple slides, is work. Okay, so by doing work, so if I lift an object above my head, okay, that requires a force. I have lifted it some distance. All right, I have given it
Potential energy.
of the gravitational kind, right? If I were to drop the object, its height, its gravitational energy is converted into
Kinetic energy.
kinetic energy. So I had to do work first, then I have given it gravitational energy. When I drop it, it now has kinetic energy. Okay, so work, let's see, we do work to give energy. That symbol is just capital W. That's the basics. The book gives some very technical definitions, and we're going to talk about the equations in just a second. But all of these things, why I put them all on the same slide, okay, all measured in joules. Named after a British scientist named James Prescott Joule, and he did some of the first real work on energy. No one really understood how important energy was. I don't even think Joule understood it, but he kind of stumbled across this idea that wasn't force and wasn't motion. It was different. And so he did the first real work on this, and so we named the unit of energy after him. The joule, let's see, is the kilogram meter squared per second squared. So this is the, these are the base units, and this is the derived unit. And so if we were to talk about gravitational potential energy, that's due to three factors. The object's mass times the acceleration due to gravity times its height above the ground. The elastic potential energy, and I encourage you to check the units. If you take kilograms times meters per second squared times meters, you get joules.
Right.
Is half kx squared. K is the spring constant, which is determined. It's an engineering thing. It's determined on the material. I believe it's like a newton per meter. How many newtons of force would it take to stretch or compress that object by 1 meter? If you really wanted to get technical, and x is how far has the stretching taken place. This is a much worse thing, but check the units. Kinetic energy is half mv squared, covered in chemistry class. Hasn't changed. Mass of the object is important. How fast it's going, make sure you square it. All of these guys are scalars. It doesn't matter if gravity is negative here. Can't have a negative scalar. Okay, so if I see you have negative energy, I'm going to mark it wrong on your test. Just an FYI, because it's a scalar quantity. Work is the force times the distance. How much force does it take to lift the object up? How high did you lift it? So this could be a horizontal distance, it could be a vertical distance, but what's important here is that force and displacement or distance have to be parallel to each other. This can be negative, and so this is a vector. Because force is a vector, when you multiply a vector times a scalar, you get a vector. That's, I think, calculus 3, but a little preview. So, like friction, for example, does negative work.
Right.
Right? We release the energy in the form of heat. Okay? So here's some of the math equations that go along with this. Once again, check the units out. There's a whole bunch of sample problems in your book. We're not going to hash those out for you on pages 226 and 227. We're going to let you do those on your own. In my opinion, energy is the most important thing. No one understood this for years. Okay? A lot of people much smarter than me happen to believe this as well. It is the most important thing. Gasoline, that's energy. Heating our homes, energy. Turning our lights on, energy. Eating, energy, right? So every science class you've ever taken should address the concept of energy.
Most do.
Most do. Biology, I know it's talked about. Chemistry, human anatomy, or space. We address energy in every one of those courses.
The problem is we don't really talk about energy in terms of physics a lot of times.
Right, and so now we have the opportunity
Right.
to do that.
And we don't talk about work in
And that's
relationship
going to be a
physics.
hard concept because work is not energy and work is not a force. They're different quantities altogether. So we're going to spend some time on that, doing some investigations, and I believe the Section 9 podcast addresses it as well.
Do we want to talk about doing no work?
Yeah, we could do that really fast.
You're pushing a wall?
Yeah, so the work equation is FD. So in order to do work, I have to apply a force, and
I have to move
I
something.
have to move it. So I can push on a wall with all my might
For weeks.
for days, my entire life. If the wall never moves, if D is 0, then according to my equation, work is
0.
0. I'm going to be exhausted,
Right.
but I won't have done any work. When you lift weights,
Right.
the goal is for work to be 0. You want to return the weight to exactly where you found it,
Right.
like when you're squatting.
Right.
If work is not 0 after you're done squatting, you're going to the hospital.
Right.
If work is not 0 after you're done bench pressing, you're going to the hospital. It's really important to return the weight where it started.
Right.
If you don't do that, you have a problem.
And when you return the weight to where you started, you've done no work.
Right. That's the hardest thing to think
Right.
about because you're exhausted.
Right.
Right. So, with that said, signing off, this is Mr. White.
And Mr. Sadler.